Howdy, folks. Here we are, Screencast number 2, 3, whatever it is. This is stardate 5/29/2014, 11:40. Your captain, Ben Leader, here to deliver. Your background music brought to you by Odessa. Today, all right, so we're talking about series and parallel circuits because more often than not we've got more than one element to our circuit. You know, it's not often that we have just one resistor that we're looking at. We have to think about many different components in our circuits. The configurations that we see most often are series and parallel. In series, you'll notice that they are lined up in a row. Parallel, they are stacked in these parallel branches. We call each one of these a branch, and you can see quite clearly they're in parallel. But what does that actually mean? We'll talk about that. In order for you to get the most out of this screencast, it would be beneficial if you would listen to me talk and then pause it to write it down. Otherwise, it's like you're in class. So I do encourage you to pause the video to write down the notes and solve problems and things like that. So what are our differences? I'm going to try to keep this under 15 minutes, but in a series circuit, the number of pathways for the current to flow is 1. You can see the current has to go through each light bulb in a row. There's no way around it. It goes through each light bulb in a row. Whereas in a parallel circuit, there's more than one way for the current to flow. It can pick a path to go down. And the path it takes is going to be determined by the amount of resistance in each of those. We'll get there. The current in a series circuit is the same everywhere, whereas in a parallel circuit, it's split up over each of the paths. Conversely, in a series circuit, the voltage is split up over each resistor, whereas in a parallel circuit, it's the same everywhere. You can look at these pictures of waterfalls and think about how those work for the current and the voltage. Think about the potential difference, the height of the hill, and where the flow is. The water flow is the current. Resistance in a series circuit is high, so these resistances are all going to stack up, whereas in a parallel circuit the resistance is lower because there are more pathways that the current can take. So if we look at power, if current is the same everywhere, then V squared over R is going to be our power law for a series circuit, and with a high resistance we get a low power. In the case where voltage is our constant in a parallel circuit, we then use I squared R for our power, and we have a low resistance, so we get a high power. Curious. Basically, when you're adding branches in a parallel, the resistance is going down, but the current gets quite high because every time you add parallel branch, the current goes up and up and up. We'll see that in just a minute. Okay, go ahead, switch the page. So here's a picture that you can look at. A single toll booth on a highway is going to provide some resistance for the cars flowing through, right? The cars are going to have to wait while one car at a time goes through. Guy can't find his visa, and everybody gets held up. If you put 3 toll booths in a row, I don't know why anybody would, but 3 toll booths in a row is going to make more resistance. Cars are going to have to wait even longer. Whereas if you put 3 toll booths in parallel, there's a lot more options for the cars to flow through, and there will be less overall resistance. Good. So let's talk about series circuits first. In a series circuit, the current is the same everywhere. There's only one path for the current to flow. In this particular circuit, I've got R1, R2, and R3. Total resistance flows through the battery. We call it IT, and then we'll call it I1, I2, and I3 through each resistor. But the current that flows in and out of resistor 1 is the same current that flows in and out of resistor 2, and same for 3. So we say IT equals I1, I2, I3. However, the voltage that the battery provides, so it gives us an increase in potential difference here. That increase in potential difference is equal to the sum of the potential drops. So we say there's a drop in potential across this resistor and a drop in potential across resistor 2 and resistor 3. Those drops all add up to equal the total resistance. The total voltage. The total resistance in a series circuit is going to be greater than the resistance of any one resistor. In fact, those resistances of our resistors add up to give us our total resistance. We call it our equivalent resistance because you could think of replacing R1, R2, and R3 with one resistor that equaled the resistance of all three of them together. The circuit would function just the same with only one component instead of three. So that's this idea of equivalent resistance, is a single resistor that could replace several resistors. Power is the total power in a circuit. It's just the sum of the powers. We know that if our current is constant but our voltages add, it follows that the powers would add as well. And so this relationship you can look at, the ratio of two resistors is equal to the ratio of two voltages equal to the ratio of two powers, because the current is constant, looking at V equals IR and P equals I times V. Take a minute now, pause the video, and work through these 4 problems. See what you can get out of those, and I'll fill them in just a second. Pause the video. Blah! Okay, hopefully these are what you found. You can think about those, but I want to move on to make sure we get through it all and you don't have to watch 2 screencasts. Come on. There it is. Okay. If you don't look at this for a minute, in fact, let me go back, pause your video, try to solve that problem, the first example there. You'll do that, I'll give you a hint, the first thing you do is find the equivalent resistance. And then with that equivalent resistance, you can find the total current in the circuit. Once you have the total current, you know that's the current through each resistor, and you can find the voltage drops across each resistor. So go ahead, pause your video, and solve that first example. Pause it now. I'm waiting. Okay, hopefully this is what you found. Found the equivalent resistance, found the total current. It's the same everywhere, 0.3 amps. And we can find the voltage using the resistances of each resistor. So the voltage drop across resistor 1, V1 is I1 times R1, 3 volts. Likewise for resistor 2, use its resistance, 6 volts. Notice here that the sum of the voltage drops is equal to the 9 volts across the battery. And then you can find the powers. Go ahead and do the next problem, the next example. So go ahead, pause your video, move on, do the next one. It's the same process. Okay. Hopefully you did that and aren't just copying it down. I can't blame you either way, but it's better for you if you don't. But so here you go. Same story. Resistances add in series. So there's my equivalent resistance. Find the current. And here's some sample calculations or some sample equations and how we find all these things. Good. Parallel circuits. These ones are a little trickier. I've written a lot on here, but let's just look. So if you look at the black wires, this battery, say it's got 10 volts across it. There's no voltage drop across any of these wires because the wires have no resistance. So it's 10 volts coming into every light bulb. And then we know the bottom of the battery is 0 volts, so there's 0 volts coming out of all the light bulbs, which means that my voltage drop must be the same across each resistor. Okay, so we say V total is equal to V1, V2, V3. Great. The currents, however, have an opportunity to split. You see I'm drawing all these blue arrows, so the total current coming through the battery reaches this first junction, we call this a junction, and some of it splits off, we'll call that I1, and then the current left to continue is IT minus I1. It hits another junction and it can split into I2 and I3. then they meet back up down here. So here's I2 plus I3, and here's IT coming back out the end again. So the sum of the individual currents, I1 plus I2 plus I3, is equal to the total. Again, the power is a sum, and the resistances, the total resistance, we can think of an equivalent resistance for this circuit, but the way we add resistances for a parallel circuit is we take the reciprocal of the sum of the reciprocals. So here we've got 1 over Req equals 1 over each resistor. So the equivalent resistance is equal to the inverse of 1 over R1 plus 1 over R2 plus 1 over R3, etc. Just something you'll have to get familiar with. And so you can think about the fact that in a parallel circuit, the voltage is the same everywhere. So R1 over R2 is equal to I2 over R1. This comes from V equals IR. Voltages are equal. And the power P2 over P1 comes from P equals V times I times V is where this relationship comes from. So go ahead, pause your video, think about these 4 cases, see if you can fill those in. It's good for your brain. Oh yeah, I'm waiting. Ah! Okay, hopefully you saw these things. That the potential is obviously the same. Smallest resistor will have the most current because current wants to flow through the path of least resistance. So the most current will flow through the smallest resistor. Conversely, the biggest resistor will have the smallest current. And you can look at those second cases. Go ahead now, pause the video, and work on the next 2 problems, the example 6 and 7, to find the equivalent resistance for those two examples. So go ahead and do that now. And hopefully you did that. So let's jump ahead. 2 ohms was the equivalent resistance for problem 6. Problem 7, the highest resistance came from a series circuit. So you add them up to get 300. The lowest resistance came from a parallel circuit. Take the reciprocal of the sum of the reciprocals, and we get about 27.3 ohms. For this last part, same story. 2 30 ohm resistors in parallel, 1 over 30 plus 1 over 30 is 15 ohms. If we have 3 30 ohm resistors in parallel, we get 10 ohms. A little shortcut, if you have identical parallel resistors, you can just divide the value of any one resistor by the number of resistors that are in parallel with each other. 30 divided by 3 is 10. 30 divided by 2 is 15. Okay, do example 8 now. Pause the video, do example 8. Solving again for the individual voltages and currents. A little bit different from the series circuit, but I think you can handle it. Think through what's constant. Go ahead. Okie dokie. So we know the voltages are the same across each resistor. So if we want to find I1, we just take that voltage divided by R1. 24 volts divided by 12 ohms is 2 amps. Same thing for I2. We get 2 amps and 4 amps. If we want to find the total current, we need to find the total resistance, the equivalent resistance. So here we have 1/12 plus 1/6 gives us 4 ohms. 24 volts divided by 4 ohms, our equivalent resistance, gives us 6 amps. That 6 amps is what's flowing here. And then it breaks, so coming down, I've got 2 amps. And 4 amps. Notice those sums add up. Alright, try number 10. Another problem, same story, another resistor. Go ahead, pause the video, work on that one. Hopefully here's what you found. Again, notice the currents add, the individual currents add up to 6 like we expect. And I want to show you the last one. So number 11 has to do with some other things, but this is what it looks like. And 5 seconds left. This is Ben signing off. I'll see you tomorrow. Bye!